In this video, I'll talk through the National 5 Chemistry Unit 1 topic of acids and bases. At the end of this video, you should be able to state whether a soluble oxide will form an acidic or alkaline solution, be able to describe the concentrations of the ions in acidic, neutral and alkaline solutions, and also explain what happens when you dilute these solutions, be able to write equations for neutralization reactions, be able to describe how to set up a titration, identify the key parts and components of a titration, and perform the calculations associated with titrations. First, we'll start with the pH scale. This gives an indication of the hydrogen ion concentration that goes from below 0 to above 14. If you have an acidic solution, the pH will be less than 7. If it's neutral, it'll have a pH equal to 7. And if it's alkaline, it'll have a pH greater than 7. You can measure the pH using an indicator solution, pH paper, or a pH meter. When it comes to making acids and alkalis, acids are made by dissolving non-metal oxides in water. Examples would include hydrochloric acid, sulfuric acid, and nitric acid. We also have the formulas there of HCl, H2SO4, and HNO3. When it comes to deciding if it's going to make an acid or an alkali, hydrochloric acid might go to example. The reason for this is that if you use the data booklet, you can see that both hydrogen and chlorine are non-metals. Therefore, non-metal oxides are the ones that will dissolve to produce acids. On the flip side, if you have a metal oxide that can dissolve in water, you will form an alkaline solution. Examples include sodium hydroxide, NaOH, and also calcium hydroxide, CaOH2. If you have a substance that will not dissolve in water, it will not change the pH. When it comes to dealing with solutions, this is a good place to talk about the different words that are associated with solutions. If something is able to dissolve in water, it is said to be soluble in water. If a chemical does not dissolve in water, it is said to be insoluble in water. Different chemicals will dissolve in different substances. So you might have something that doesn't dissolve in water, but you can use something like acetone or ethanol, and that will be able to dissolve it. If you need to check the solubilities, you can use page 8 of the data booklet. And this shows you various different metal compounds. And it gives you the key to tell you that VS is very soluble and I means insoluble. So this will come in handy for some of the questions we'll look at today. The solute is the substance that is being dissolved. The solvent is the substance which does the dissolving. And a solution is the mixture produced after dissolving. Let's pick an example from here. If we had aluminium bromide and we're dissolving that in water, aluminium bromide would be the solute, water would be the solvent, then the aluminium bromide solution would be the solution that we're making. In this question, we are asked which of the following oxides, when shaken with water, would give an alkaline solution. We can approach this in two different ways. First thing I would do is think, well, soluble non-metal oxides make acidic solutions. Therefore, we are looking for a metal oxide that would form an alkaline solution. We can then go to the data booklet. Here we have calcium oxide is soluble in water and nickel oxide is insoluble in water. Therefore, for this question, calcium oxide is a soluble, so it dissolves in water. It's a metal oxide, and that would give us our correct answer. C and D are both non-metal oxides that would produce acids. Nickel oxide is insoluble, so would not affect the pH. In this question, we are asked about the pH value that would be obtained from zinc oxide. As it is a metal oxide, if it dissolves in water, it would form an alkaline solution. Going into the data booklet though, it does not dissolve in water, therefore it will have no effect on the pH of water. That means that it's going to stay at pH 7. If it was a non-metal oxide forming an acid, then A would be a good answer because acids have a pH less than 7. Alkalis will be above 7, so C and D would be correct for a soluble metal oxide. Next, we're going to talk about water. When we have a solution of water, the majority of the water particles will be molecules, valently bonded hydrogens to an oxygen. Some of them, though, will be present as ions. This is where they've either lost or gained electrons. This explains why, despite water being a covalent compound, it can conduct electricity. At the bottom, we've got the equation showing this splitting up or dissociation of water, where water molecules, H2O, break up into hydrogen, H+, and hydroxide, OH- ions. Acidic solutions will have more H pluses than OH-, so greater concentration of hydrogen ions than hydroxide ions. If we're dealing with neutral ones, neutral solutions will have equal concentrations of H+ and OH-, and alkaline solutions will have more hydroxide ions than hydrogen ions. If, for example, the acidic one sticks in your head better, more H+ than OH-, alkalis is just the opposite. in neutral it's equal. And we'll talk about what happens when you add water to these solutions. When it comes to when you add water to an acid, you will decrease this concentration of the acid. You'll increase the pH towards 7, which is neutral, becoming less acidic, heading up towards 7. And it will also decrease the concentration of hydrogen ions. So pH up towards 7 and concentration down. When it comes to an alkali, we're now dealing with something here at pH 14. You again decrease its concentration. You'll decrease the pH towards 7, and you'll decrease the concentration of the hydroxide ion. So in both cases, the pH moves towards 7. In both cases, you're decreasing the concentration of the relevant ion. So hydroxide for alkalis and H plus for acid. Here we have to pick the correct description of an alkaline solution. Alkaline solutions have a pH greater than 7. They have more hydroxide ions than hydrogen ions. They have both hydrogen and hydroxide ions, ruling out A and B, and then more hydroxide, so D would be a correct answer. In this question, we're asked to pick the line that describes what happens to the solution of hydrochloric acid when water is added to it. First thing we need to remember is that acidic solutions will have a pH less than 7. They have more H pluses, hydrogen ions, than hydroxide ions. When we add water to an acid, its pH is going to rise from somewhere below 7 towards 7, and it's going to become less acidic, so its concentration is going to decrease. Next, we've got a very important reaction involving acids. This is where an acid and a base react together. We have acid plus base makes salt plus water. Examples of bases include metal hydroxides, oxides, and carbonates. Ammonia is another example of a base. And a base is a substance which neutralizes an acid. You would have heard me flip-flop between base and acid throughout this video. Or an alkali is a base that's able to dissolve in water. Let's look at two examples of bases. We have calcium and copper oxides. Both of them are able to neutralize an acid. When we look at their solubility, calcium oxide is soluble. This means that calcium oxide is a base that can form an alkali. Copper oxide can only be described as a base because in this question we're asked which compound would not neutralize hydrochloric acid, and we have a few different examples of sodium compounds. Bases neutralize acids. Bases include hydroxides, oxides, and carbonates. Looking through these, we've got metal carbonate, metal hydroxide, metal oxide. That means that B is the odd one out because it is not a base. Sodium chloride is a salt. That's what you form when you neutralize an acid, but it wouldn't be used to neutralize the acid. When it comes to naming the salts, the first part of the name comes from the alkali or base that was used, and the second part of the name of the salt comes from the acid. So we'll go through a couple of these ones. So for example, if you have hydrochloric acid and sodium hydroxide, you would make sodium chloride. Potassium hydroxide, sulfuric acid, potassium sulfate. You can kind of see how they fit quite nicely together. You might in exam questions get one that's not quite as familiar. It might be a different metal, it might be a kind of obscure acid. The naming scheme starts the same. Take the first part of the alkali and that goes first in the salt. Take the acid and tweak it slightly, and then that'll give you the second half of the name. You could be asked to write word equations for these reactions. So here we've got metal hydroxide plus acid makes salt and water. You add calcium hydroxide, nitric acid, that will make calcium nitrate and water. An example of a metal oxide and acid making salt and water would be copper oxide, sulfuric acid making copper sulfate and water. The third substance we're going to use is a carbonate. And in this one, we're still making salt, we're still making water, but we also form carbon dioxide. So if you had sodium carbonate, hydrochloric acid, sodium chloride, water, and importantly, carbon dioxide as well. Questions to this, they could ask you here, which of the following is not a salt? Well, a salt you would make during a neutralization reaction. Usually, I'm not going to say it's always going to happen, but usually in these questions, if they're asking you for something that's not a salt, 3 of them will be salts, and 1 of them will be a base. The base is used to make salts, and those can be oxides, hydroxides, and carbonates. Metal oxides, hydroxides, carbonates. Looking through these ones then, D would be my answer here because that is an example of a metal hydroxide which acts as a base and neutralize the acid. Another way you can look at it is you can work back to a combination of an acid and a base that would make the other 3 of them. So one example would be calcium oxide and nitric acid, making calcium nitrate water. Make sodium chloride, we could use sodium hydroxide and hydrochloric acid. And to make potassium sulfate, we could use potassium carbonate, sulfuric acid, make potassium sulfate water and carbonate. You could have the other combination. So in the first one, we could use calcium hydroxide, or we could use sodium oxide or something like that as well. That's kind of two ways we can approach that type of question. In the next question, we're asked about which of the pairs of chemicals would react to produce a gas that turns lime water cloudy. Our gas tests that we need to know about, we need to know that carbon dioxide turns lime water cloudy, hydrogen burns with a squeaky pop, and oxygen relights a glowing splint. We're looking for a combination of chemicals that would make carbon dioxide. The bottom two reactions, we have a metal and an acid. Metals plus acid make salt and hydrogen. Not going to make carbon dioxide. For one, there's no carbon involved anywhere in C and D, so you can't make carbon dioxide from that. The next one, we're going to make salt and water from B. Again, just thinking it here, we could actually get it from the fact that, well, we've only got copper, oxygen, sulfur, and oxygen, and hydrogen, sulfuric acid. So again, there's no carbon involved. You can't make carbon dioxide. The answer would be A. Metal, carbonate, and acid would make salt water and carbon dioxide. Next one, we're going to discuss spectator ions. These are ions that remain unchanged by the reaction. They're present in the same state at the beginning and the end of the reaction. States would be your solids, liquid, gases, or in solution, aqueous. We can use reaction equations to identify these spectator ions. So looking at metal hydroxides and acid, if we had something like sodium hydroxide and hydrochloric acid, we make sodium chloride and water. We want to see, are there any chemicals that appear on the left-hand side and right-hand side of the equation that we can cancel out? We have Na plus in solution, and we have Na plus in solution or not. This means we can cancel them out. The OH minus doesn't appear on both sides, so that has to stay. H plus doesn't appear on both sides, so has to stay. But the Cl minus, the chloride ions, is on both sides unchanged. That means we can simplify this down to H plus OH minus goes to H2O, or we could write it the other way around, just depending on what we want to do it. Moving on to a different set of chemicals. Here we have calcium oxide and sulfuric acid. Let's have a look again. Well, we've got calcium still 2 positive and it's still AQ. That can cancel away. We have SO4, 2 minus, AQ on both. Cancel them out, leaving us with O2 minus plus 2H plus goes to water again. So we still get water and the end of it. It's just a slightly different way of getting that. And the third chemical we're going to use is metal carbonate. This time it's sodium carbonate and nitric acid. Going through here, well, I can see sodium is Na plus AQ on both sides. Also got the nitrate, which is NO3 minus, again on both sides in the same state, leaving us with CO32 minus plus H2 positive goes to H2O plus CO2. These are the 3 ionic equations without spectator ions for different neutralization reactions. Important point to take from here is that during a neutralization, you will always produce water. You're looking for an acid, a base, and we're making water out of it. In this one, we're asked to decide on the spectator ions. I'm going to do this one in a slightly different way, which is what I'm going to look at. The original chemicals are all in solution. They're all AQ. If it's in solution at the beginning and it's a spectator and doesn't change, it's still going to have to be AQ on the other side. So both the potassium, the K plus, the nitrate, NO3 minus, have not changed. They are still in solution. They will be my spectator ions. Now we could still go through it the same way and look at, well, there's NO3 negative AQ still there, then same for the K plus. But kind of skippy part would be, well, if it starts off as AQ and it's a spectator, it will still be AQ, aqueous, at the end. Next, we're going to deal with calculations associated with solutions. And this one I'm going to deal with N equals C times V. The number of moles of a solute in a solution can be calculated from the concentration and volume of that solution. That's in the data booklet, N equals C times V. What do those stand for? Well, N is the number of moles in moles. C is the concentration, typically in moles per litre. And V is the volume, which would be usually in litres. Oftentimes, you'll be given the volumes as centimetres cubed, and you have to divide that by 1,000 to turn it into litres. In this question, we're asked to calculate the number of moles in 500 centimetres cubed of 1 mole per litre solution. First thing I'd want to do is to write down what I've been given. Well, the concentration is 1. The volume I want to turn into litres. Divided by 1,000 gives you 0.5 litres. Data bucket tells us that N equals C times V. Pop the numbers in. 1 times 0.5 gives you 0.5 moles. Just like that. Moving on, we're asked for concentration this time. So starting off, identify what you're told. We're told the number of moles is 0.1. The concentration is what we're to calculate. There's 50 centimeters cubed, which is 0.05 litres by 1,000. N equals C times V. Shuffle it around. Well, C then has to equal N divided by V. You need to find a way of rearranging that suits you. So one way of doing it is to say, well, at the moment, C multiplied by V, move V across and divide by it, N over V. Pop in the numbers, 0.1 divided by 0.05, 2 of them that fit in. That gives you 2 moles per litre as our answer. If you're asked to calculate the volume, here we're told there's 2 moles of the solution. Concentration is 1 mole per litre. And we want V. Well, if N equals C times V, then V equals N over C. Pop the numbers in. 2 divided by 1 just gives you 2 litres of solution would be used in this one. Here's an example that also takes into account the N equals M over GFM calculation from previous topic. So at this point, we're asked to calculate the concentration of solution in moles per litre. To get concentration, we want to use N equals dV, so C equals N over V. Looking through, do we have a number of moles? We don't. To get the number of moles, we need to, in this question, use N equals M over GFM, because we are told the mass of the substance we're using. We need to work out the GFM of copper sulfate. They give us the formula, CuSO4. You can find those values on page 7 of the data booklet. Copper 63.5, oxygen 16, and sulfur 32. Working through the numbers, taking into account we've got 4 oxygens, gives us a total of 159.5 grams per mole. N equals M over GFM, so the 3.19 over that number we calculated gives us 0.02 moles. This now means that we have enough information to work out C equals N over V. 0.02 divided by 0.1 will give you 0.2 moles per litre. Next, we'll talk about a very important technique for chemistry, which is a titration. This is where we use a solution of accurately known concentration to help figure out or determine what is the concentration of the unknown solution. They involve standard solutions, which is a solution of accurately known concentration, a definition that comes up every so often. The types of titration that we will be mostly focused on are acid-base titrations, where the concentration of the acid or base can be determined by accurately measuring the volumes used in a neutralization reaction. Because the majority of the chemicals we're using are colourless, we can add an indicator to show when the reaction has finished. And this diagram from Compound Chem shows us various different options for pH indicators. Phenolphthalein is quite commonly used because it's got a very distinctive colour change from nothing to pink. We also have a few different ones that if you continue doing chemistry, you might come across later years. So how do we go about setting this up? Well, we'd use a pipette, which is the piece of equipment on the left. We would transfer a specific volume of chemical 1 into a conical flask. The burette, which is on the right-hand side, which is the kind of taller, longer one, that's filled with chemical 2, and we record the initial volume that we are starting at. You then add the chemical 2 to the conical flask until the colour changes, and we record the volume at the end of the reaction. The volume used, which is the difference between the start and the end values, is called the titer value. And this is the value that we start to use in our calculations. You'd be asked to repeat the titration until you have concordant results. And concordant means that they're within 0.2 centimeters cubed of each other. So they're in close agreement to one another. If this was your results from your titration, we would need to figure out, well, what are we going to use in our calculation? Often, but not always, the first result will be a rough result. We'll try to get our eye in, how much do we need, and we can start doing it a bit more carefully next up. And we would then look at results 2 and 3, 24.5 and 24.3. They are within 0.2 of each other. This means we'd use the average of those two concordant results to use in our calculation. And that would give you 24.4 centimeters cubed as your average. And that's what you then use in your NCV calculations moving forward. A couple of little notes. So number one, if all three of them were within 0.2 of each other, you would use the average of all three of the results. If titration 1 and 3 were concordant with each other, you would use them and then you would ignore the second one. So in this example, I'm not doing the second and third because they're the second and third. No, because they are within 0.2 of each other. Here's an exam style question. They have told us that they're carrying out a titration experiment to determine the concentration of sodium hydroxide solution. We have our results. Now in this one, the table is shuffled round. This time, the column we care about is the right-hand column. We care about the volumes used. We're going to compare them to each other. We're going to see, do we need to average 2 of them, 3 of them? The 15.6 is just too large a value compared to the other values. So we want to take the average of the first and second titer, add them together, then divide it by 2, gives us an average of 15 centimeters. In some questions, you'll be asked to use information about chemical 1 to determine information about chemical 2. One example would be here, we're asked to calculate the concentration of hydrochloric acid if 25 centimeters cubed was neutralized by 25 centimeters cubed of 1 mole per liter sodium hydroxide. In these types of questions, we want to decide which chemical should we start with and why. Which one are we asked to talk about at the very end? Well, we're asked about hydrochloric acid. We'll need to start with the sodium hydroxide. Another way of doing it is which one are we told more information about? Well, we have a volume and concentration for sodium hydroxide. So we're going to start with that one. So for sodium hydroxide, which is NaOH, we are going to use N equals C times V. C is the concentration of 1. V is the volume, which is 25 centimeters cubed. Hopefully you've remembered that you need to divide that by 1,000 to turn it into litres. It would be 0.025. And 1 times 0.025 is just 0.025. In these questions, it's similar to ones on NMGFM. We need to find a way of relating the number of moles of NaOH to our HCl, chemical 1 to chemical 2. We have the balanced equation here, and what this is telling me is that it's a 1-to-1 ratio. For every 1 NaOH, we need 1 HCl, and that means it's the same number of moles on both sides. We now know the number of moles of HCl. We were told the volume back at the very top. And that means we're going to do C equals N over V, the 0.025 from the previous part, divided by the 25 centimeters cubed, which is 0.025 litres. That gives us a concentration of 1 mole per litre. In this next example, what I've done is I've made the numbers a little bit more difficult, and we'll see the ratio as well in a second. We're going to start with the nitric acid because we're told more information about it. We're going to do N equals C times V, 0.5 moles per litre, and 33 centimeters cubed needs divided by 1,000 to give 0.033. Multiplying them together gives us 0.0165 moles. This stage here, I try and keep as many digits as we can, so it's just 3 significant figures, so I'm just going to put them all in. The balanced equation this time looks like this. When we're comparing chemical 1, the HNO3, to the calcium hydroxide, the Ca brackets OH2, it's a 2-to-1 ratio this time. This means we need to half the number of moles. Then, moving on to the calcium hydroxide, we were asked for the volume this time. The volume equals number of moles divided by concentration. We just worked out the number of moles. Divide that by the 0.75 that we're told in the question. Pop that into your calculator, gives us 0.011 litres, which we could convert into centimetres cubed as 11 centimetres. It depends on what the question's saying. If the question asked us for centimetres cubed, give them it in centimetres cubed. If not, either one would be acceptable. In this exam style question, we've got more information. There's a bit more going on. We're going to try and get our eye in and figure out what information we care about. So, job 1 for me, which chemical should we start with? I'm going to start with the iodine and work out the moles of the iodine because I'm told the volume and the concentration. Or we're asked about vitamin C, so we'll save that for the end. N equals C times V from the data booklet. The number of moles is 0.005 and the volume is 16 centimeters cubed or 0.016 litres. Dividing 16 by 1000. Pop that in the calculator gives us 8 times 10 to the power of minus 5. We could write that as 0.00008 or 0.8. Easier, nicer, I think, neater looking at it this way. Stage 2, but we need to get from iodine over to vitamin C. So let's look at our ratio. It is a 1-to-1 ratio because there's no balance in numbers, no big numbers in front of the chemicals. That means it's the same number on both sides. So that 8 times 10 to the minus 5. Shuffling on, we want to work out the concentration of the vitamin C with N equals C times V and C equals N over V. Our number of moles is what we just worked out, the 8 times 10 to the minus 5, and divide that by 25 centimeters cubed. Divide that by 1000 gives you 0.025. That'll give us an answer of 0.0032 moles per. In questions like these, I am very, very rigid on I will turn my centimeters cubed into litres every single time. If someone wasn't to do that and didn't change the first chemical into litres, also didn't change the second chemical into litres, you will still get the same answer. However, if the question wanted how many moles of vitamin C, your answer would be wrong. So in my view, it's better to do it every single time, and then that way you're keeping everything right, regardless of what the question wants you to do at the end. In the data booklet, there is another equation that can help with those titration calculations. I don't like using this because it's very, very limiting what it does. Like the question we just did, it would be very good. It would get you to the answer straightforwardly. When you start asking for, well, what's the number of moles instead of the concentration, or what's the mass instead of concentration, this falls down for me. In my book, I much prefer to use a NCV twice kind of thing. Because there are those limitations to that one, that's why I prefer not to deal with that. If your teacher does that, if you're happy with that, then you'll still be able to get the answers for that. Personal preference for me is to ignore that and pretend it doesn't exist. Next thing we could have asked about is how we prepare samples of salts. If we have performed a titration using acids and bases, we've neutralised the acid, we've made the salt, we can dry off those solutions, remove the water, and be left with a dry sample of salt. So we could take our sample, put it in an evaporating dish, heat it with a Bunsen burner, and that would remove the water from it. If you're using an insoluble base, something that doesn't dissolve in water, we can do it in a slightly different way. What we could do is we could add excess of the base, neutralise all the acid, you then filter off any remaining excess base, and then take the filtered solution and evaporate it off to be able to get the salt. The question might need you to look up the solubilities of the chemicals to decide, would you need to filter off any excess, or could you go straight to the evaporation? Depends very much on which combination of chemicals we're dealing with. Here's an exam style question covering those techniques. Here they're asked to determine the concentration of a copper sulfate solution. They've given us the steps that we do. They're asking us about how do you actually get to the dry sample of the salt. So in this one, we've got just our solution. We want to evaporate off, heat it up, boil off the water. We want to remove any water and leave the dried sample behind. You could be asked to complete a diagram, draw a diagram, show how this could be done. But the main point is you want to remove any water from the sample. That brings us to the end of the acid and base topic. Hopefully now you're more confident in deciding whether an acidic or alkaline solution will be formed. Talking about the ions in each of those types of solutions. More comfortable describing the concentrations of ions in those solutions, and also how adding water affects the pH and the concentrations. You're able to write equations for neutralization reactions and also talk about the titration and calculations associated with those. Thanks for watching. Goodbye.